All right, welcome to night 2 for the Celestial Navigation class. We are missing a couple people. One person emailed me and told me they weren't going to be here. The other one should be here, but let's go ahead and start anyway. So I'm going to be curious to know how you guys did on the homework. But tell you what, let's start in the slides here. I have a slide definitely just for that. Let me go to sharing my screen here. Okay. All righty. So the agenda for today is we're going to review last time's material and ask how you did. And then the majority of the time tonight is going to be spent learning how to use the sextant and learning how to adjust the sextant and all those things that you need to do. And so the goal is that by the time we finish today, we should be able to repeat what you did last time, where last time you took the star measurements using this little poor man's tool right here. But by the end of tonight, you should be able to do the same thing, only this time using a sextant, and hopefully get much better numbers than you got last time. And then once we know that, then we'll start the process of setting the smartphone aside and doing the math ourselves without the smartphone. Oh, good. Here comes Andrew. Okay, so good. Perfect timing, Andrew. All right, so let's start with Paul. Were you able to, let's start with your poor man's sextant results. Were you able to get even close to your actual position?
Yeah, I put myself in North America.
Okay, that's reassuring. Were you able to get within Utah?
I think I did a couple of different things, and I think one put me in a triangle that Utah was kind of in a good part of, and another put me in, I think, Nebraska.
Uh-oh. Okay. All right, Alex, how about you?
So
Were you
there were
able to
some
get in Utah?
imperfections.
Yes, I actually got it to North Salt Lake. I
Oh,
was
wow.
extremely surprised. Yeah.
That's pretty good. Now you live in South Salt Lake, right? Is that correct?
I live in Orem,
Oh, Orem.
so
Okay. All right. Well, at least you're in the
definitely
right
close
half of
enough
the
for me.
state.
Yeah, I was blown away. I didn't think based off, yeah, and I live in a third story like condo. So
Mhm.
I was like, I don't know, I'm probably 25 feet high.
Well,
So it worked.
when you're using this tool, the eye height doesn't even matter. Doesn't even come into the equation. Andrew, how about you?
The night that I went was cloudy, so
Okay. All right. Okay. And so then my next question then would be, how did you do? Let's see, come on. All right. So how did you do on problem number 18? When you took the numbers from the workbook and put them into your smartphone, were you able to get numbers anywhere close to this? I'll just throw it out for any one of you.
no, I didn't get to that.
Okay. All right. Paul,
So, so I spent today working on that, and one of my things got me real close to that. And one of my, I use two different apps, and one of them got me to 22.57 and 118, 16, which were not real exact. And I'm kind of mystified by that.
which app was the one that performed better?
It seems like it was Celestial Nav, the cheaper one. But I'm going to go back through it and try it a few more times, because in one case I kept it wasn't accepting the date. I put it in and then it would go back to a different, and I found out it was because on a different screen it had something up with a different date and time, and I just need to work on it and figure out the little kludgy parts probably.
Yeah, every app has its own little peculiarities. It gets a little bit frustrating sometimes. Alex, how about you?
Yeah, mine, using the app that I found, it got to 22 degrees 31.1 south, and then 119 5.8 west.
Okay, great.
So
Yeah,
pretty darn close.
yeah, that's wonderful. Now, notice even these two apps that you see on the screen right here are not the same. And
Right.
that's because of the planet problem that we talked about last time. If you're going to be using a smartphone, it's probably best to just leave the planets out because they are a little tricky for the algorithms to accurately predict where they should be. If you just stick with stars only, you should get excellent results with pretty much any app that you use. Okay, well that's good. That's very encouraging. So let's go ahead. Right now, there were a couple of review problems that I tossed out there just in case you wanted to do a quick review of sea-based, non-celestial navigation. Did any of you have any questions that you wanted to ask me about those review problems?
Yeah, I did. On the time one, which is 16. 16? Yeah, 16. Okay. So on page 13, for most of these, I was just kind of going, okay, if it's like, okay, if it's like 1,600 hours in California, we'll just kind of start adding some numbers, 6, 7, 8, 9, 20, 22, 23. Yeah. And I did that with that one. I did that with 17. But when I did it with 16, it didn't work. Because it's -9 is the correction. And then I got, let me check the answer to make sure I'm where I know I'm talking about. Just a minute. Okay, and so the answer says it's 3 a.m. But I was thinking if it's noon local time and it's a -9, how do I get to 3 a.m. from that?
Okay. All right, so let me open up a whiteboard here. And okay. All right. So here's the Earth, and here's Greenwich. And so let's say that it's noon at Greenwich. So the sun is right here. And so as the sun goes around, okay, there's 360 degrees in 24 hours.
Uh-huh.
All right, so that means there are 24 time zones in the world. If we ignore political considerations and just go based on the clock only. So 360 divided by 24 tells us, okay, so each time zone is 15 degrees wide. Okay, so if Greenwich, let's say that the sun is right there, and let's suppose that Greenwich is in the middle of its time zone. So that means over here, it'd be 7.5 degrees to the west. Here it'd be 7.5 degrees to the east. So this is one time zone. And so the next time zone, the center of the next time zone is going to be at 15 degrees. Center of the next time zone after that's going to be at 30 and then 45 and so forth. Just keep adding Okay, so if this person is at a longitude of 138 degrees east, okay, so we're going east, not west here. All right, so then so we need to figure out how far that is. So 138, right? Is that what I said? Okay, so 138, let's divide that by 15. Okay, so that's 9.2 time zones. And so, okay. So that means that it's 9 hours different for them. So if it's noon for them, then that means that it's still early in the morning in Greenwich. And so it's 9 time zones different. So 12 minus 9 is 3 a.m.
Okay, go up to like 14. 14 is if the time's 9 o'clock in the 9:22 in Utah. What's universal time? I wonder if I'm reading this. So Utah is -7. So I just figure 9, 10, 11, 12, 1, 2, 3, 4, 4 o'clock, 1600 hours. That's the right answer according to the book, is 4 p.m. 16.
Now Utah is to the west, whereas 138 on problem number 16, it's 138 degrees east. Is that perhaps the reason you're not getting the right answer?
And it did the same thing. Noon, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. But it was actually, but I was supposed to go the other direction. That's why I'm a little confused. It's probably a stupid little mistake I'm making, but I'm not picking up on it.
Yeah. Yeah, just keep thinking
I'll just
about it.
work on it on my own time.
Yeah. I mean, the way I think about it is each time zone would be 15 degrees wide. So if this person is living at a longitude of 138 degrees, that'd be 9.2 time zones. So that means they're going to be the 9 hours different. So yeah, think about it. And if you still don't get it, email me and let's work it out. Let's work it out in private that way.
Right.
Okay, so let's go back into here. Okay, so I'm hoping that you are comfortable with this chart. Now, I really like this chart. This chart was definitely made by a sailor as opposed to an astronomer. The thing that I like about the chart is all these lines. So that, I mean, like for instance, let's say that you can find the big, oops, wrong one. Let's try that one. Let's say you can find the Big Dipper, which, you know, most everybody can find the Big Dipper. If you look at the handle of the Big Dipper, it forms an arc. And if you follow that arc, then it takes you to a star, which coincidentally is named Arcturus, which is a total coincidence, but kind of a nice thing. And if you continue that arc, then you get to a star called Spica, and so forth. So if you can find one thing on the chart here, then you can use these lines to kind of walk you through and find the rest of them. So when you guys went outside, if you looked to the west, or, you know, if you haven't yet done it tonight, try it. Go out there as soon as class lets out. And what you'll find just in the west is you'll find that Orion will be setting in the west. Now, it's because it's setting, it's not going to look quite like this. Instead of being like this, it's going to be more tilted like that. That's one of the problems with this chart is it doesn't exactly align with what you're going to see in the sky. When Orion comes up in the east, he's lying on his back. When he's directly south of you, he looks like this, and then when he's going down in the west, he kind of goes down face first. But anyway, if you can find Orion, which most people can, then use these lines to find the ones around him. So, you know, we've got this kind of an egg-shaped thing that goes around Orion. So if you if you start here at his belt and then find his right foot, which is Rigel, and then just go up, and then there's a bright star there, which is Aldebaran, and then continue around the loop, and you'll see this nice circle of stars that's all around Orion. So these lines that you see here, you know, if you can find one feature, you can just follow the lines to get to the other stars. And it's really, really convenient. I really like this chart here. So I'd recommend that you guys spend some time just getting familiar with it. Recognize that when you go out and look at the sky is going to look a little different from this. But if you spend a couple nights out there in the spring, and then again in the summer, and again in the fall, I think you'll find that after a while, the stars become your friends. And it's kind of cool. I mean, many times I've gone outside and, you know, I look at the sky and, you know, and I see Vega and Deneb, and I say, well, wait a minute, Altair should be right here, but I'm not seeing Altair. What's the deal? Where are you? And then I realized that there's just a dark cloud there covering it up. And after a minute, you know, the cloud moves away, and there's Altair. Good. I was getting worried about you. I mean, literally, they are your friends, and it's really cool to get comfortable with the night sky. I like that a lot. Okay, let's move on.
Doug,
Yeah.
do you have a PDF of that?
Yes. I can send that to you. Now it's in your book. It's page whatever on your book. But if you'd like, I can send you a separate PDF of just that one page. Be glad to do that.
I'd
And
like that too.
I'm a little old fashioned. Can I buy a copy of the notebook rather than just having the file online?
Well, you can print it out and have it
Okay.
and take it into Kinko's and have them bind it for you. That's what I did with this. Okay. So this is the exact same as the file that you got. I just printed it out and took it to Kinko's, and they put this nice little spiral binder on it and put in this clear front cover. It's quite
Okay.
nice. Or
Okay, thank you.
just take the file to Kinko's and they'll print it for you. Except, do they even call themselves Kinko's anymore? I think they call themselves the FedEx office now, but
FedEx, yeah, FedEx Office Services or something like that.
yeah. Okay, let's see. Okay. All right, so let's just do a little quick review because well, it's super important that everybody's totally comfortable with these ideas. Okay, so when we're doing celestial navigation, our goal is to find out how far are we. Let me switch to a different color, maybe works better. Okay, so this point right here is the point that's directly underneath the star. Now the picture here is a little confusing maybe. Imagine this star is off at infinity. Okay, and so the person right here, the star is directly above their head. And so this is what we call the geographic position of the star. So if you were located right here, the star would be exactly above your head at what we call the zenith point, but you're not located right there. You're located right here. And so if we can measure the zenith angle, then this zenith angle will be equal to our angular distance away from the geographic position. That's the key. And then once we know that, then we can draw a circle around it, and we know that we're somewhere on that circle. So the zenith angle is what we're really after, okay? But it's hard, if not impossible, to measure the zenith angle with the kind of accuracy that we're going to need. So what we do is we instead measure the star's altitude above the horizon, because that is something that we can measure with very, very high accuracy. And so once we get that, then just take 90 minus it, and that'll give us the zenith angle, which is what we want. Okay, so what we do is we measure the altitude of the star. And the sextant is a wonderful, wonderful tool for doing that. And so tonight's goal is to figure that out. But before we do that, let's just do a quick review. So a mariner's quadrant is what people used for a long time, which is basically the exact same as the protractor that you guys used when you did last night's homework. There's another instrument called an astrolabe, which is used especially if you're measuring the sun. Because let's go back up to here. I mean, I'm sure you can imagine the problem if you want to measure the altitude of the sun and you're using either the Mariner's quadrant or if you're using our nifty little protractor. I mean, you can see what the problem is going to be, right? I try to use this to measure the sun. What's the problem going to be? Yeah, very good. Yes, I'm going to go blind, okay, because the sun is too bright, right? So what one of the things that they did in order to get around that problem was they've got this astrolabe. And so it's kind of like the Mariner's quadrant, but it's got this little, whoops, wrong color. Let's go back to black. Okay, so it's got a little device right here that, and you can see better right here. And it's got a little notch cut in it right here. And then right here is a board basically. And so if the sun is right here, then you're going to see the shadow of this thing with a notch on it right here. And so what you can do is there's a notch right here and a notch right here. And so what you're going to do is you're going to turn this little pointer here, it can pivot. And if you turn the pivot until the shadow of this notch lines up with that notch, then you can just read off of here what the angle is. And so you can get it without going blind. So it's a nice way to get around the problem of the sun making you blind. There are other techniques that you can use that I don't think I'm going to talk too much about. The Kamal is kind of an interesting one. If you have these different knots in them, let's see, you got these different knots in the string, and so, well, maybe I will say just a little bit about it. So each one of these knots corresponds to some port that the sailors want to get to. And so then what they can do is they can align it so that here's the horizon and here's the star, and preferably the North Star. That makes it the easiest, Polaris. Okay, and so so each one of these knots here would line up with the latitude of some port that they're trying to reach. So they sail north or south until Polaris lines up exactly right when they've got the appropriate knot in their teeth. And then they know that they're at the right angle. So there's been some really creative techniques used over the years. But the one that we're going to do, let's just skip over these. Okay, so the sextant is the one that we want. So let's focus in on that. All right, so first off is how do you get around the problem of measuring the sun without going blind? All right, so on a sextant, you have these solar filters, and most, if not all of you guys have the Mark III. So that's what these guys are for. These are solar filters. And so what you can do is you can look at the sun. Now, we've got two sets of filters. We got this set of filter blocks the sun in one path, and this one blocks them in the other. So I'll come back to this in a little while, but first I want to make sure you understand about the two different optical paths that a sextant has. Because if you don't understand that, then the rest of what I'm going to say doesn't make sense. So let's jump into that. Okay, so yeah, let's go back here. Okay, in your sextant, if you've got a Mark III, or if you've got a Davis Mark III, then for sure you have what is called a split horizon mirror. And so what that means is that, so let's get these filters out of the way completely. So when I look through here, if I look at the little glass plate that you see right here, and I'm looking at, say, the horizon, then what I will see, if my sextant is set for 0, in fact, everybody do that right now. Get out your sextant, set it so that the dial reads, so that the 0 on the bottom part is lined up with the 0 on the top part. and then look at something that's really, really far away. And if you look through this piece right here, this piece of this piece that I'm pointing to right here, it looks like it's a piece of glass. And so if you were looking at the horizon, what you will see is something that's best explained. Let me open up my my thing here. Okay, so if you look through the sextant at something that's really far away, and if your sextant is set for 0, you will see an image here where what you see on the left side of the image is the light that is coming directly into your eye without doing any bouncing around. The left side here is the light that goes directly into your eye. But on the right side, that's very different. What you see on the right side, the light comes in here, hits the mirror up here, comes down here, hits this mirror, and then bounces into your eye. And so if your sextant is perfectly calibrated, then the image you see on the right side and the image you see on the left side are going to line up so perfectly that the right side, what you see in the sextant, if you look at it, you would swear that it's a transparent piece of glass, but it's actually not. It's actually a mirror. You're actually not looking through it. What you're seeing is light that comes in here, bounces there, and goes there. And the best way to really understand it is to have it be a little bit misadjusted. So let's come here. Okay. All right. So what you see on my screen right now is you can see that there's a little bit of an offset. The right side is a little bit higher than the left side. So when you look through your sextant, which I'd like everybody to do right now, okay, if you look at the mirror, you'll see that the image that you're seeing in the mirror is probably, in fact, almost certainly not going to be lined up with the image on just to the left of it. So what I'd like you to do now is take the bottom dial here and just play with the bottom dial and see if you can get the image to line up. Now, if you're looking at something that's close, like in the same room as you, it may be a little bit hard to get them to line up. But if you're looking at something really far away, if you have an open window and you can look out the open window at the mountains that's really far away, you should be able to get it so that the right side of the image and the left side of the image line up so well that on the right side, you'd swear that you're looking through a window, not through a mirror. Are you able to get that?
Yes.
Okay.
Yes.
All right.
I was confused for a second because I thought I was supposed to have 2 pieces of glass until I realized my view has the mirror on one side and actual unfiltered on the other side. So
Yes, that's it.
understood.
Exactly. All right. You got that. Okay. So, so if you were looking at the horizon that was perfectly, that was essentially infinitely far away, and if your sextant was adjusted absolutely perfectly, then you would see something that looks like this. You would see that the horizon would be a perfectly straight line. But if your sextant is misadjusted at all, then what you're going to see is this. And remember, when you put the numbers into the smartphone, it asked you what the index error was. Well, this is index error. This is a case where the mirrors are not quite adjusted right. So what you could do to fix that is you could adjust the mirrors. And in fact, yeah, let's go ahead and do it now. So I want you to look through the sextant at something that has a good horizontal line to it. It doesn't have to be the horizon. I mean, if you've got some blinds in your room, or if you've got a window ledge, or just look at anything that has a horizontal line in it. And then there's these, you see these two screws right here on the upper mirror? Okay. Play with the upper screw while you're looking through it. Okay. And you see how the image moves up and down?
Yes.
Okay, good. All right. So that is the way that you correct for index error. So if you were out on the ocean or near a large body of water, what you would do is you would look at the horizon, and you would and make sure that your sextant is set for exactly 0. That's really important. It's got to be exactly on 0. And then just play with the screw on your mirror until the left edge and the right edge line up, and then you will no longer have any index error. Okay, so now let's see how a sextant works. Let's suppose we want to measure some object. Right now, what you're seeing on your screen is the sun, but it could be some other object. Okay, so now here is where the filters become really important, because if you try to look at the sun without any filters, you're going to go blind. So tell you what, let's hold off on the filters. Let's come back and get the filters later. So on my picture here, I have it so that it's the sun, but let's pretend it's a star instead. So that way we don't have to worry about the filters. Okay, so if you look at a star, what you're going to see is this image here. So this dot in the middle of there is the star. And it doesn't matter if you go a little bit to the right so that the star is over on this side, or you go over on the left. You know, you can kind of swing left and right, and the star will move left and right. And the important thing is that it won't do this. If you've got index error, so let me clear that. So if you've got index error, when you position the star here and then swing the sextant, it's going to come here, and then all of a sudden, boom, it's going to go down here. That's what it would look like if you have index error. But if you don't have index error, then what will happen is the star here, swing over here, star here, and it'll be exactly the same as if you were just looking through a window at the star. Okay, so once we've got the star aligned like that, now what we're going to want to do is we're going to want to move the sextant ever so slightly to the left, so that, let me open this back up again. Okay, so we want to point the sextant so that the star is over on the right side. So what we're doing is we're looking at the reflected image of the star. So we're seeing that so the starlight comes here, hits that, comes here and hits that. Okay, so now what we're going to do is we're going to do what's called bringing the star down to the horizon. Okay, so let's imagine that I've got the star, so it's positioned in the right side of my field of view. So the star is in the mirror. Okay, now here's the important thing. I'm going to, with my left hand, I'm going to hold the pivot arm, and I'm just going to hold my left hand rock steady, and I'm going to rotate my right hand so that the sextant comes down like this, but my left hand is rock steady. So the pivot arm does not move, the sextant does. And if I do it right, and I bring this down carefully, even though my sextant is coming down, I'm still going to see the star in the right side of my image, because this arm is not really moving. And so even though I tilt this back and forth here, I'm still going to see a star in the right side of my image. So that, in theory, does that make sense? Okay, so I'm going to bring this down until when I get it to this point right here. Now I'm going to see the horizon on the left side, but I'm going to see the star in the right side. So let me show you what that's going to look like. Okay, so I start off, the star looks like this, and now I start rotating the sextant until it comes down a bit. And then when I get it just right, I'll see the star through the mirror, and it'll be lined up with the horizon that I'll be seeing on the right side. Okay, and once I get it to there, then I can just read off of here what the angle is. Now, the best way to understand this is to actually do it. So I have, where to go here? Okay, here. All right, so I want you guys to pretend that what you see on the screen right now is the thing that you want to measure. So let me get yellow here. Okay, so let's say that this is the star. So ignore the sun for right now. Let's say this is the star that we want to measure. And let's say that this is the horizon line. So we want to bring that star down to the horizon line. Okay, so remember, start off with your sextant set for 0. And then look through there. Now here, you're going to have a little bit of a problem because the sextant is designed for things that are infinitely far away. So if you're actually really close to the screen, when you look through here, the star is not going to be where it should be. It'll be a little bit below. If you point to where the star should be and then look down a little bit, can you see the star there? Or actually, a better way to do it is instead of putting the sextant at 0, put the sextant at like -10 or -15. Okay, can you get it? Can you guys get it to where you can see the star reflected in the mirror on the right side?
And like
Okay.
the bottom 0 moves towards your face. Is that negative?
Yes, right. So that's
Okay.
negative. So that'll help it so that when you look through the star, you'll actually be able to see the star in the mirror part there. So let me go back to here again. Okay, so can you get the star so you can see the star in the mirror?
Yes.
Okay, so now hold the movable arm with your left hand, and then hold your left hand rock steady. Do not move your left hand, but start rotating your right hand so that you tilt the sextant down. And as you do that, you'll see that you can bring it down to where on the left side, where you're not looking through the mirror, you will see the horizon line, but on the right side, you can see the star.
Yes.
Ah, good. Okay, you got it.
Yeah.
Okay, how about you?
Now what?
Okay, so once you've got it on the horizon line, then
Yes.
how about you, Alex? Have you got it on the horizon now?
Yeah.
Okay. All right. So now what we're going to do is we're going to read the angle. So if you look down here, this will tell you what the angle is. So on the bottom, there's a 0. And so just look up above the 0 to see what number does it line up with. Now, because we're measuring something that's really, really close, these numbers are not going to be real. Because remember, the sextant is designed to measure something that's infinitely far away. So let me show you something that's a little bit more realistic here. Let me give you, okay, so let's suppose that this is what it looked like, okay? We measured a star, we brought the star down to the horizon, and when we look at our sextant, this is what we see right here. Okay, so what you want to do is you want to look for the 0 on the bottom, and then you ask yourself, what number does that 0 line up with? So what do you guys see when you look at the screen here?
26.5.
Okay, so you guys agree it's somewhere between 26 and 27, right?
Yes.
And it does look like it's approximately a half, but we can find out better than just calling it a half. Okay, this way of aligning the lines here it's called a vernier scale. And if you've ever done any machining where you've used vernier calipers or anything like that, then you've seen this before. The spacing of these lines that are on the bottom half here is ever so slightly different than the spacing up above here. They're designed in a very clever way so that there is one and only one place where the line on the bottom and on the line on the top will line up exactly. Okay, so if you look over here, you'll see they don't quite line up. They mismatch, right? If you look over here, you'll see they don't line up. They mismatch. But as you work your way in here, and as you work your way
It's
in
like
here,
11.
they get closer and closer together. Yeah, so you guys agreed that's the one that lines up?
Yeah.
Okay. All right. So what we do is we look at the bottom one, not the top one. And
Oh.
so what we can see here is that it is the 30. Actually, you know, you could argue whether it's you could make a good argument here for whether this is the one that lines up best, or maybe this is the line that lines up the best. You could kind of argue that. Okay, so if it was this one that lines up the best, that would correspond to 30. And so that would mean that the angle that we measured is 26 degrees and 30 minutes. Now,
Oh.
if this one right here, let me clear out the screen here. If this one right here was the one that lined up the best, then we would say that it's 26 degrees and 28 minutes. Each one of these marks on the bottom here corresponds to 2 minutes. Now, when I look at it, I can't quite tell whether it's the 28 that lines up the best or the 30 that lines up the best. So what that means, if that's the case, if the 28 and the 30 are both kind of lined up equally, what I would do then is I would call it 29 minutes. I would say that the angle that we just measured here is 26 degrees and 29 minutes. But I mean, you could argue. So maybe it's 28 minutes, maybe it's 30 minutes. So we've got plus or minus about 1 minute's worth of uncertainty, but we're quite sure that it's not 27, and we're quite sure that it's not 31. It's somewhere in that range there. So you see, so the accuracy of the Davis Mark III is about plus or minus 1 minute, which remember is 1/60th of a degree, which is pretty darn good.
Mm-hmm.
So that makes sense to you guys?
Yep.
Okay. All right. Now, if you were going to measure the sun, so let's go back here to our practice night sky here, right? So let's say that instead of measuring the star, okay, hang on a sec, I got to turn on my annotation. So instead of measuring the star there, we want to measure the sun. And now we haven't yet talked about how to do this without going blind. I will talk about that in a minute. But let's suppose that we have Superman eyes that can withstand looking at the sun. So I want you guys now to bring the sun down to the horizon. And what you're going to find is that once you get the sun down to the horizon here, I mean, ideally, theoretically, this is what you'd want, because you want to know where the center of the sun is. But you can't do that with the kind of accuracy that we need. So what we're going to do is, instead of bringing the center of the sun down to the horizon, we're going to bring it down so that just the bottom edge of the sun is just barely kissing the horizon. That is what we're going to do. And then when we put the numbers into the smartphone, this is the reason why the smartphone is going to ask us. It's going to say, did you measure the lower limb of the sun, or did you measure the upper limb of the sun? Because you could do it either way. Most people do lower limb, but it really doesn't matter. Okay, so practice that now. Practice bringing the sun down to the horizon. And again, because we're measuring something that's only a few feet away from us, the number that we're going to get is going to be way off. But The technique is the important thing. So are you able to get it to where the sun just barely kisses the horizon there?
Yes.
Okay.
Interestingly, it's almost at 0.
Yeah, but remember, we started off at like -10 or something like that. So when you're measuring something that's not infinitely far away, yeah, 0 is not really 0. But if you were doing this with something that was infinitely far away, then it would work.
Sure.
Okay, so now I'm going to show you something that is also very important. So let me get rid of my writing here. Okay. Okay, let's go up here. Okay, once you've brought the sun or the star down to the horizon, you want to rock the sextant back and forth, and the reason is this. So let's say that I've brought the sun or the star down to the horizon, but what if I'm not holding my sextant perfectly vertical? What if I'm holding my sextant? Now this is greatly exaggerated, obviously, but what if it was tilted like this and I just didn't know it? I'm going to get a horribly wrong, or I'm going to get a wrong answer. Okay, so what I need to know is I need to know what the angle is when the sextant is perfectly vertical. Okay, so the easy way to know when the sextant is perfectly vertical is when you bring the thing down to the horizon, rock the sextant back and forth like this. And when you do that, what you will see in the screen is basically this. Whatever the object is that you brought down to the horizon, you'll see that as you rock the sextant back and forth, it makes kind of a U shape like that. And when it's at the lowest part of the U shape, that's when you know that the sextant is perfectly vertical. All right, so let's go back to our practice screen here. Go back to this one right here. Okay, so I want you to work. Let's go back to and use the star again, and let's bring the star down to the horizon. And this time, when you get it down to the horizon, I want you to rock the sextant back and forth so that you can see what I mean when I say it goes through a kind of a U shape. Can you see how that works? You see the U shape that it goes through? Okay, so, okay, good. I can see you guys are definitely doing the rocking here like you're supposed to. All right. So what you want to do is you want to adjust the arm here so that when the thing is going through its U shape, when it's right at the bottom of the U, that is when it's just sitting on the horizon. And the rest of the time it's going to be up above the horizon, but just at that one point there, that's when it's going to be sitting on the horizon.
Mm-hmm.
Okay. So that's the measurement that you want. Okay. Thumbs up.
Yep.
Okay. All right, good. So that's how you use the sextant. Now there are still a few more tricks we need to talk about, but that basically that's it. Now let's find out how can we do that without going blind if we want to measure the sun. Okay, so let's go back here to where we talk about the mirrors. Okay, so on an Astra 3B. Okay, so with an Astra 3B, I've got two sets of mirrors. I've got one set of mirrors that is designed to block the sunlight that is going through the upper path. Okay, so if I put these here, then, and let's say I'm looking at the sun. So the sunlight comes in here, bounces off this mirror, goes through the filters, hits the mirror down here, and then comes into my eye. So I'm not going to be blinded by that. But I've got another problem, because remember, on the left side, that's the light that just comes right straight in, right? So in that case, I need another set of mirrors. So I've got this separate set of mirrors right here. So these are the mirrors now. So if I've got my sextant set for 0, and if I'm looking at the sun, I need to have both sets of mirrors in place, right? So let's say that I found the sun, and well, did I call these mirrors? I think I called these mirrors, didn't I? Filters is what I meant. Hopefully you guys knew what I meant as opposed to what I said. Okay, so I've got both sets of filters in place. All right, so I've got my sextant set for 0. I'm up here, I'm looking at the sun. I've got both filters in place, but I can still see the sun because you know, the light does get through the filter. Okay, so now what I'm going to do is I'm going to bring my sextant down. And if I hold this rock steady and bring it down, so I'm still going to see the sun over on the right side, and I need that filtered. But now I get down to the point where on the left side I should be seeing the horizon. But with these filters in place, these filters are so dark, I'm not going to be able to see the horizon. So what I need to do is, okay, let's say I've got both filters in place. I'm bringing the sun down. I'm getting pretty close to the horizon, but I can't yet see the horizon. Now this is where it gets a little tricky. So I need to reach up here very carefully without losing the sun. And I need to flip these filters out of the way, but I need to keep these filters in the way. So now on the left side, I can now see the horizon. And on the right side, I see the filtered sun. Okay, so that's how it works with an Astra 3B. Now, how does it work with a Davis Mark III? Okay, so these filters that you guys have right here, these are the ones that are going to filter the sun as it comes, bounces off this mirror, goes down to there. These are the filters that are going to protect your eye from the light that's coming in straight, that's not bounced off of there. So let's say we're going to look at the sun. So I want to put these filters in place, and I want to put these filters in place. And I set my sextant for 0, and I look up here until I find the sun. And now I get the sun, so he's positioned in the mirror over on the right side of my field of view. Hold this thing rock steady, and I start pivoting like this. So if I do it right, I'll keep the sun in my view over on the right side. And now I get down to where I should be seeing the horizon, but I can't because it's too dark. So now I just reach up and flip these filters out of the way, but keep these where they are. And so now I can see the horizon on the left side, and I can see the filtered sun on the right side, and bingo. I can measure the sun without going blind. That makes sense?
Yes.
Okay. All right, so it takes a little bit of practice. When you are measuring stars, what you're going to find is that okay, so you're going to get the star in place. You got him in the mirror here. As you bring him down, you're probably going to lose him, especially if you're on a boat and the boat's getting rocked around a lot. You know, you bring the star down and you got about halfway down, and then a wave hits you, and then the star is no longer in the mirror. And you say, oh, rats, and you look around and you can't find it. So you have to go back and start again, put it back to 0, go back up there, you know, and it may take you 2 or 3 tries before you can get it all the way down to the horizon. Now, once you've got it on the horizon, then if a big wave hits you and you lose sight of the star, you're actually okay, because once you got it down on the horizon, just leave this where it is, and then just look at the horizon, and then just kind of scan back and forth on the horizon. And when you get in the right place, the star will appear in the mirror. So you don't have to bring it all the way down from the sky again. You know, he'll be pretty close there. Okay, so now, so I've got the star, he's on the horizon. Now I'm going to do my left and right rocking and tweak this until I get it right. And then bingo, I now know the altitude of the star. Make sense? Okay. All right. Now, remember last time we talked about the fact that the number that we get from the sextant isn't really accurate because of things like the eye height and because of things like the refraction of the light as it comes into the air. So there are a bunch of correction factors that we need to apply to this number, but the smartphone will do all that for you. So if you just tell the smartphone what your eye height was, it'll automatically correct for that. And then the refraction error, that it just automatically does that. It doesn't even need to ask you anything. It just automatically corrects for that. So if you're using the smartphone, then you can just take these numbers, put them in the smartphone, and bingo, you will get a good position and much, much more accurate than your other one. Okay. So let's see. Let's talk about how you might do that if you live in Utah, which all of you guys do. Okay, let me come down to here. Remind me, I need to talk about the difference between a split mirror and a whole horizon mirror, but I don't want to do that right now. I want to finish a thought here. Okay, so let's suppose, so these are the various errors that need correcting. So we'll come back, we'll talk about those some more. So let's, okay. All right, so as long as you understand what we just said, and if you're satisfied letting the smartphone do all the math for you, then you're there. You can now navigate by the stars. And so your homework, one of your homework assignments for tonight is to do that. So how could you do that? Well, if you're in Utah, there are two wonderful lakes here in Utah that will work just very well for you. What you need is a large body of water. And so go there either just a little bit after sunset or a little bit before sunrise, when the stars are still visible. The sky is dark enough that you can see the stars, but it's also light enough that you can see the horizon. And so then bring the stars down to the horizon. And now it has to be a body of water because it needs to be a true horizon. If you have mountains or hills or anything like that, the horizon that you see is not really a true horizon. It's only going to be a true horizon if you have a large body of water. So where could you go to do that? Well, if you go to the Great Salt Lake, then you could just go to the Great Salt Lake Marina. Now, the reason I've got this circle here with 3.5 nautical miles is because of this factor right here. This equation, D equals 1.17 times the square root of H, that tells you what is the distance to the horizon depending on how high your eye is above the ground. So if your eye, or above the water is what I should say, above the water. If your eye is 4 feet above the water, then when you look at the horizon, that horizon that you're seeing is 2.4 nautical miles away. If you're 6 feet above the water, it's 2.9 nautical miles away. Okay, so what this means is that if you go to a lake, as long as that lake is more than about 3 nautical miles wide, then when you look at the water line, that water line that you're seeing is a usable true horizon. If the lake is less than 3 miles across, then the water line that you're seeing is not really a true horizon. So let's say 3.5 miles just to be safe. I mean, actually, if you're 6 feet tall, 2.9 nautical miles is good, but let's just add a little on there just to be safe. So what we want is someplace where the distance from where we're located, from that point, we've got at least 3.5 nautical miles worth of unobstructed water. So if we were to go out to the Great Salt Lake, I don't know if you guys have been to the marina out there. So here's a satellite view of the marina. If you go out there and you walk out to the very edge and you stand out here on the jetty, If you look to the north, well, you've got more than 3.5 nautical miles of water to the north. And in fact, if you look to the west, you've got more than 3.5 nautical miles of water. Even though over here you got the Stansbury Islands, the Stansbury Mountains, that's okay, because the water that you see is more than 3.5 nautical miles away. So any star that is north or west of you, you could measure. Anything to the east or south, yeah, forget that. But if it's north or west of you, or northwest, or anywhere in this arc that you see right here, you can measure stars and you will get a valid number. Okay, what about Utah Lake? All right, well, if you go to the Provo Marina, this arc that you see here, any star that's located in this direction, you could measure it and you'd get a good usable number. So that's a nice wide range there. If you want to measure any stars that are located to the east of you, well, just go over here to anywhere on the west side of the lake. Now I've got it set here for Pelican Point, just because it sticks out the farthest. So if you're standing at Pelican Point, any star that's located in any one of these directions there, you could measure that and get a good usable number. If I don't know if you guys go to either the American Fork Marina or the Linden Marina. This is the American Fork Marina. So if you were to go there, okay, any star that's in this range right here, you could measure. Okay. So if you go to either the Great Salt Lake or Utah Lake, I think you'll find enough stars in those usable arcs there that you should be able to get some good readings and put them in your smartphone, and you should be able to get a number that's pretty darn good. Now with the Davis Mark III, as we saw a few minutes ago, there's about plus or minus 1 minute of uncertainty. So, 1 minute is 1/60th of a degree. But even with plus or minus 1 minute of uncertainty, that's good enough. You should be able to find your latitude to within, or latitude and longitude, to within about 30 or 40 miles, quite accurately. Okay. And you might think, well, 30 or 40 miles, that's pretty bad. Well, it's actually not bad at all. I mean, let's suppose you're sailing to Hawaii and you're using your Mark III in order to find your latitude and longitude, and let's say that you're off by 30 or 40 miles. You'll still get to Hawaii. I mean, Hawaii's got big enough mountains, big tall enough mountains. You can see those mountains from a long ways away. So even if your latitude and longitude is off by your 30 or 40 nautical miles, you'll get close enough, you'll see Hawaii. You'll make it. Okay. So you guys confident that you can go out and make some measurements?
Sure. So old-time sailors with sextants, if it was the middle of the night, they wouldn't be able to really take measurement unless they had enough starlight or something to make out a horizon.
Yeah, you're
or a
absolutely
dawn
right.
and dusk thing, or a
Yeah,
day with the sun.
Yeah, you have to be able to see the horizon. Now, if the moon is out, if it's a crescent moon, yeah, maybe not, but if it's a half moon or more, that the moonlight will give you enough light where you'll be able to see the horizon there. But if the moon's not out, then forget it. You can only make measurements about a half hour after the sun sets, or about a half hour before the sun rises, plus or minus a little bit. And during the daytime, you can of course measure the sun. And now you want to get more than one reading in order to be able to triangulate your position. So if all you've got is the sun, then hopefully you've got a little bit of time on your hands. So what you can do is you can measure the sun in the morning and then just sit and read a book for a while the sun moves. And then so a couple hours later, measure the sun a second time. And then, and so there's your 2 lines. And then if you want, you can wait a couple hours.
You were frozen for about the last minute.
Oh, that's not good. Okay, so let me go back and say that again. So let's say that it's daytime and all you've got is the sun. So what you can do is you can measure the sun in the morning when it's over here, wait a couple hours when the sun's over there, and then bingo, you got 2 lines of position. You can figure out where you are. Now, if you're on a boat that's moving in between those 2 measurements, that complicates things. But if you're not, I mean, if you're sitting on the shoreline at Utah Lake, then yeah, you can do that. Take your 2 measurements and bingo, get your position really, really well. Now, there is a special technique called doing a noon sunshot. And we are going to be talking about how to do a noon sunshot, but not today. That I'm going to save that for later. So there's a couple things about sextants that I kind of skipped over because I wanted to get you familiar with how sextants work. Let's go back now and let's talk about a few things that I kind of skipped over. Okay. All right. So index error. Okay. Different sailors have different philosophies about what to do if your sextant has index error. So what you see on the screen right here, this is assuming that you've got a sextant that's not been adjusted right, so it's got index error. Your sextant is set for exactly 0, and you're looking at the horizon. And so you look through your sextant and you see this left-right mismatch right here. You see the right side horizon does not line up with the left side horizon. Okay, so you've got index error. What do? Well, what I do is I fix the index error. I adjust the screws here until I no longer have index error. There are sailors out there who they're afraid to touch the mirror. They think that they might break something, and so they're afraid to touch the mirror. So what they do is they just measure what the index error is, and then they just live with that amount of index error. So let's suppose that this is what we got, okay? And we're one of those sailors who's afraid to adjust your sextant. And so what you can do then is you look through here and you see this, and then what you do then is you just turn this arm a little bit here until the left and the right horizons line up, and then you look to see what it reads here. And let's say that it reads maybe 5 minutes of angle, and so then you just make a note and say, well, my sextant has five minutes of index error. Okay, and then when you put the numbers into your smartphone and it asks you what is your index error, that's what you put in. Okay. Now, me personally, I'm not afraid to touch my mirror. If I have index error, I correct it. Okay, but not everybody does. Now, speaking of correcting index error, the better sextants like the Astra 3B, if you look at the mirror and you see here's the adjustment screw, the adjustment screw is hidden inside of there's a little cylinder there. If I were to grab that and twist it, it doesn't do anything. You have to have a special tool that can get inside here, because oops, if you look at your Mark III, it's very, very easy to correct for the index error, but unfortunately that means it's also very, very easy to mess up the mirror, right? You just too easy to accidentally tweak that. So with the Astra 3B, the adjustment screw is inside a little protected cylinder. So if I want to fix my index error, I need a special tool, which I keep right here. Okay. So I just put this tool in there and then use the tool and adjust it. Okay. So if I had lost my tool, then I would just have to live with the index error. I wouldn't be able to fix it. Okay, let's see what else are things that we kind of skipped over.
Doug, when
Yeah.
you do the index error, just adjustment of the mirror, it's using the horizon, right?
Definitely, yes. Absolutely,
Okay.
positively. Must be using the horizon. If you try to adjust this for anything that's not at the horizon, then when you go to measure a star, which is infinitely far away, your sextant's going to be misadjusted. So yeah, got to be looking at the horizon.
Blocks away. And then I thought, that's probably not the way to do it. So thank
Yeah.
you. That makes sense.
Yeah, it has to be really, really far away. Now, if you were to look at the mountains, I mean, if you're more than about 5 or 10 miles away from the mountains, then that's pretty good. All right, so here you can see the recessed screws that I mentioned. These are the ones on the Astra 3B where the little thing that you need to adjust is in there and is protected. So you have to have a special tool to get to it. Now, one of your homework problems tonight is going to be problem number 19 in the workbook. In problem number 19, we are assuming that the sextant has index error, just because I want you guys to have experience working with that. And so here's where you got to be really careful. The different smartphone apps, they use different terminology here that can be kind of confusing. So in problem number 19, when I set it up, I did it so that when the sextant should read 0, what it actually does read is negative 0.3 of a minute. Okay, so what that means then is that what it means then is that all of the readings are going to be 0.3 minutes lower than they really should be. Okay, so in a case like that, we would say that the index error is negative 0.3. We would say that the index correction is positive 0.3. So here you got to be really careful. Some of the apps will ask you, what is the index error? Others of the apps will ask you, what is the index correction? So make sure you know which one is which for your app. And also, if you've got the Android app, instead of saying negative 0.3 or positive 0.3, what they do is they say, is it 0.3 off the arc or is it 0.3 on the arc? Which is just kind of an old time sailor convention that I think is confusing and I don't like it, but a lot of people do it. So if somebody says that your index error is off the arc, what that means is that it reads negative when it should read 0. If it was on the arc, that means it reads positive when it should read 0. So as you can see, my little bottom here, life is just so much simpler if you just adjust your sextant mirrors properly so you have 0 index error. It makes life so much simpler. So that's what I recommend you do. Okay. Why am I thinking that I left something out? Oh yeah, the whole horizon mirror. Yeah, I knew there was something that I left out. Okay. So on the Davis Mark III, it works the way that we've just described. But on some sextants, they don't have the same kind of arrangement on the mirror. Instead of using what's called a split mirror, some sextants, they make it so that the mirror that's right here is a half silvered mirror. So what I mean by that is, imagine that you've got a sheet of glass, and in order to make it be a mirror, what you do is you evaporate silver or some kind of metal onto the surface of the glass. Okay, and if you make it so that the metal is so thick that it's completely opaque, what you have now is a 100% reflective mirror. But you don't need to make it that thick. What you can do is just evaporate a little bit of metal on there, but not so much that it completely blocks all the light. So imagine that you've got this half silvered mirror. So when you look through it, half of the light that hits it gets reflected, and the other half of the light just goes right straight through. Okay, so what you can do then is you can get a sextant that has a whole horizon mirror, or if you've got an Astra 3B, you can swap them out. In fact, let me do this. So I have both mirrors. Okay, so this right here, I don't know how well you can see it. So this is the traditional split mirror. It's clear glass on this side. I mean, you can see looking through there. So there, I think I've got it where you can see reflections on the lower part, and you can see through it on the top part. Okay, so this side here is clear glass. This side over here is full mirror, 100% mirror. So this is the traditional split horizon mirror. What I've got mounted on my sextant right now is actually a whole horizon mirror. This is one of those half silvered mirrors that I told you about. So the left side and the right side, the entire thing is just half silvered mirror. So why would you want that? And how would that work? Okay. So let's suppose you've got a full horizon mirror on there. Then what you're going to see is that, so let's see, here's the light. Okay. So imagine the sun is up here. So the light comes down, hits this mirror, and comes through you. And no matter where the sun is, the sun might be over here, the sun might be over here. You will see the sun everywhere, but you're only going to see half of the light, because remember, this is a half silvered mirror. So when the sunlight comes in here, only half of it gets reflected towards you. The other half just goes right straight through. So you've lost half of your light. Now look at the light that's coming in from the horizon. So the light coming in from the horizon, it comes here. Half of the light goes right straight through, and half of it gets reflected down here. So again, you've lost half of your light there. But it's kind of convenient, because now when you can tilt the sextant to the left or to the right, and you'll still see the sun everywhere. If you're using a split mirror, as long as the sun is over here, you'll see it fine. But if you tilt the sextant too far to the left, where the sun should be right here, you're actually not going to see it there, because there's no mirror there, right? So if you're measuring the sun, then a full horizon mirror is a little bit more convenient. Not a whole lot, but enough that it's kind of nice. Okay, so full horizon mirrors are wonderful for measuring the sun. They are not wonderful if you're measuring a dim star, because, so imagine this is a star that's not very bright to begin with. Okay, so the sunlight or the starlight is coming, it hits this mirror, half of the light goes through, and only half of the light comes back to your eye. So the star was pretty dim to begin with, and now right here you've already lost half of the starlight, and so it might be to where you're not able to see the star anymore. So when people ask me which mirror they should get for their sextant, if you can only get one mirror, I would definitely get the split horizon mirror, because the split horizon mirror works much better for stars than the full horizon mirror does. And it does a good job on the sun too. I mean, the full horizon mirror is a little bit more convenient when you're measuring the sun, but you can do the job just fine with the split mirror. But if you're measuring a dim star, then definitely the split mirror is the one you want, not the full horizon mirror, Okay. Now on the Davis Mark III,
So what did they use 100, 200 years ago in old timer days?
they had the split mirror. I mean, they didn't have any choice, because half silvered mirrors didn't exist back then, at least to my knowledge. Okay, so I think we've covered everything for how sextants work. Let me just go through. Oh yeah, there is one other thing. None of you guys have a quote unquote traditional sextant, but some of you might get one at some point. So you need to know how to read a traditional sextant. So let's go back and let's remind ourselves, how does the Mark III work? Remember this, whoops, before I touch my screen, I have to turn on annotation. Okay, so remember the vernier scales here? So the way they work is that if you look at the lines on the bottom and see how do they line up with the ones on the top, there's only one place where they line up. All right, well, if you've got go ahead. Okay, I thought I heard somebody asking a question. So if you've got a more traditional mirror like an Astra 3B or whatever, okay, it kind of works the same way. So let's suppose that we've used a traditional mirror, and let's suppose that this is what the arm looks like after we brought the star down to the horizon. So if you look right here, you can see that the arrow here is in between the 29 and the 30. So we know that the angle that we've measured is 29 point something. Okay, it's somewhere between 29 and 30. So we want to know, where is it between 29 and 30? All right, so then what we do is we look over here. You can see that the 0 line lines up with, if you look to see where it lines up, you'll see that it's somewhere between 42 and 43. You guys agree when you look at it? The 0 line,
Yes.
okay, somewhere between 42 and 43. Okay, so what that means then is that the angle that we just measured is 29 degrees and 42 point something minutes. Okay, well, we want to say, so we say to ourselves, well, what is the something? Because these sextants, they are capable of measuring to 1/10 of 1 minute of accuracy. So I know it's somewhere between 42 minutes and 43 minutes. So if only I could find out more precisely. Well, in fact, we can. So we use the vernier approach here to do this. What we do is we say, okay, look at these guys on the right, look at the guys on the left, and they've been arranged in such a way that only one of them is going to line up perfectly. So look at that and tell me, and when I say which one lines up perfectly, I mean the numbers on the right. Which number on the right?
5.
Yeah, lines up perfectly. Okay, so you guys agree that 5 is the one that lines up perfectly? Okay, so what that means then is that the angle that we just measured was 29 degrees,
47 minutes.
42.5. What did you say? You think it's 7?
Oh, yeah, it's 47 minutes, right?
Well, the 47 is where the 5 is lined up. I don't argue that, but where the 0 lines up.
Oh, I see. I see what you're saying. Okay.
Yeah. So where the 0 lines up, that's the one that tells us how many minutes it is. And
Got
so if the 5 is the one that lines up over here, we don't care what number it lines up with over here. We just
Oh, okay.
care which one over here lines up. Okay, so this would correspond to 29 degrees, 42.5 minutes. So you can see that with these more expensive sextants, you can get readings that are more precise than you could with the Davis Mark III. But I mean, do you really need that much precision if it's just an emergency use? You know?
Probably not.
Yeah, not for emergency use. I mean, if you didn't have a GPS, you know, if you were back 100 years ago and this was your only means of figuring out where you want to get, then yeah, I would definitely want the extra precision. But if all we're looking for is to use our sextant for emergency use, I'm thinking the Davis Mark III is going to do the job for us. Okay, so I think we are good then. So remember all of these errors that needed correcting? So, okay, so remember that if you're using the smartphone, it will automatically take care of all those for you. So don't need to worry about it. Okay. Now, So we have now reached the point where if you're willing to use the smartphone, you're golden. You can go. You can start navigating right now, as long as you're willing to let the smartphone do all the work, the mathematical work for you. But I'm presuming that you probably want to know how to do it yourselves. And so my goal from right now onward is we're going to learn how to set the smartphone aside and how to do the math ourselves. So is that something that you guys want to do?
Yeah, can you do filters just a little bit more?
You bet. You bet. Do you have a specific question? You're muted.
You're muted,
Why-
Paul.
Why is
Oh,
there one?
yeah, if I remember right, there's two different filters on each thing.
Right.
So what's the deal with that?
Okay. Remember how there are two optical paths?
Yeah,
There's the path where the light comes in, hits the upper mirror, hits the lower mirror, and then goes to your eye. So you need one set of filters that can filter the light that goes through that path.
yeah, why are there two?
Oh, yes. Thank you. That's an important thing that I should have mentioned. I forgot. Thank you. The reason there are two is because sometimes the sun might be kind of partially obscured by a thin cloud. And so if you give it the full filter, that might be too much. And so what you can do is you can just put in maybe just one filter only. Okay. And so then, so if the sun was not obscured by a cloud, the sun would be uncomfortably bright. It won't be dangerous. You won't go blind, because just one filter all by itself will be enough to block out all the UV, but it might be uncomfortably bright. Okay. So
Doug?
then if you put both of them in there, then it's good. Okay. So
Doug, one is red and one is green.
yeah.
Does
Yeah,
one
so-
have better filter properties than the other if the sun's brighter, or does it matter which one we use for
No,
partial?
just whatever's more comfortable for you. I mean,
Okay,
if the sun is not obscured by any clouds at all, then you're going to want to put both of them in.
right.
place.
But if it's partially obscured, then do you use the red or the green one?
What I do is I just experiment and see which one I like the best.
Okay.
Yeah. And I don't remember. I mean, to be honest, it's been years since I used the Mark III. I mean, I always use the Astra when I'm out there. Now with the Astra, it's actually got 4 filters. Okay. Yeah, I've got 4 different filters to choose from. If I put all 4 filters in place, then that's too much. Even if the sun is not obscured by any clouds at all, 4 filters is too much. So what I generally do is, just play around with them until I get the sun to the right, to where it's comfortable to look at. Okay. And then the same thing with the other set of filters that goes through to block the optical path that did not get off here. Again, with the Astra 3B, I've got 3 different filters to choose from. And if I put all 3 of them in there at the same time, that would be too much. So I just play with them until I get one that's comfortable. Okay. Now, occasionally, if you're measuring a full moon, you might find that the full moon is uncomfortably bright. Well, with the Astra, with the Davis Mark III, you wouldn't have any problem, but the Astra's got a really nice telescope on it, a good high quality telescope. So if I'm looking at the full moon, that might be a little bit uncomfortably bright. So there's one filter in here that's just the right filter for a full moon, just to bring it down to where I can look at it without having to squint. So my only advice there is just play with them and see what feels most comfortable to you. That answer your question?
Mm-hmm.
Okay. All righty. Okay, so these are the various errors that need correcting. So the number that you read off of the sextant is not actually the altitude of the star. And so these are the reasons why the number is not actually going to be right. Okay, so your sextant might have some index correction that you need to take care of. You will definitely have some eye height correction that needs to take care of. And by the way, you're going to see the word dip used an awful lot. Dip is just another name for eye height correction. If the star is relatively low on the horizon, then you're going to have some refraction correction that you need to take care of. If you're measuring the moon or Mars or Venus, then you might have some parallax correction you need to take care of. If you measured the sun or the moon, remember, if this is the horizon, what you really want is you want to know, in theory, you'd want to bring the sun down like that, so the center of the sun is right on the horizon, but you can't do that with high accuracy. So what you do instead is you bring the sun down to where it's just barely kissing the horizon. And so then you have to correct for the fact that the sun is higher than it should be. So that's what we call the limb correction. And temperature correction, in theory, you need to take care of, but in reality, you only need to worry about it if you're at really, really low temperature or if you're at really, really low pressure, which almost never happens. So I don't even worry about that. But in theory, those are things you do need to worry about. Okay, so let's see, let's skip over here. This is all stuff we talked about. Okay, so here, let's all just pat ourselves on the back and say, congratulations. If you're willing to let the smartphone do all the math for you, then you can graduate right now. You can now navigate by the stars. But we presumably want to know better. So let's see, let's skip over all this. We talked about this. Okay, so let's learn how to do things without relying on the smartphone app. Okay, so remember when you looked in the smartphone, it gave you a bunch of numbers that I didn't talk about. I just kind of ignored them. But now they're going to become relevant. There's this number that is that the Celestial app on your iPhones, it calls HA. And then there's HO, and then there's HC. And so what do those mean? Okay, well, let's find out. Okay. Here is another homework problem that I want you guys to do. We'll do part of it together here, but you need to finish it up at by yourselves as a homework assignment. Can everybody open up the workbook and look at problem number 67? Okay, so it's on page 32 of the workbook. Okay. So in problem number 67, we are going to do all of the corrections ourselves. So you can see that what we've got here are two different objects that we have measured. We've got a star named Fomalhaut, and we've got a planet, which is Mars, and we've measured them. And so we want to correct for all of the different things that need to be corrected for. And we're not going to use the smartphone. So what we do is we start by just taking the sextant reading and we put that in this box right here. And H is the letter that's used for the altitude. And so HA is the, I'm sorry, HS is what I meant to say. HS is the number that comes right straight off the sextant. All right, so if you look at the problem statement here, it says that for the star Fomalhaut, the sextant reading was 46 degrees and 13.5 minutes. So we're just going to go ahead and write that in. That is the number that we're going to call HS. Now what we need to do is we need to correct for any index error. So if our sextant had any problems. So if you look up here, okay, here the problem statement says that our index error is plus 0.2. Okay, so what that means is our mirrors are misadjusted And so when a number, when we're looking at the horizon where it should be 0, they don't line up right. And in order to get the left and right edges to line up right, we have to put it to a setting of 0.1. So every number that we read is going to be, or I'm sorry, 0.2. So every number that we read in the sextant is 0.2 minutes higher than is accurate. So no problem. We're going to put in an index correction of negative 0.2 minutes. All right. Next thing we need to do is we need to put in what's called the eye height or the dip correction. Okay. So remember the idea here is that when you measure an angle, if you are actually swimming in the ocean when you measure it, then the angle that you measure is good. But if you're anything above the water, even if you're only 4 feet above the water line, the angle that you measure is actually bigger than the real true angle by about this much, by these numbers that you see here, depending on how high you are. Okay, so there are some pages in the Nautical Almanac that will tell you what correct. Okay, so when you go sailing, you're going to want to buy a Nautical Almanac for whatever year it is. They publish a new one of these every year. So if you're sitting there right now saying, but Doug, you didn't tell us to buy a Nautical Almanac. Well, the reason I didn't tell you to is because the textbook has some sample pages built into it. So everybody get out your textbook. And I want you to turn to page 246 in your textbook. Okay. All right. So what you see on page 246 was taken from an old Nautical Almanac that was back in the year 2005, I believe, is when it was. Okay. Yeah, it was 2005. Okay. So all of the problems in my workbook and all of the sample problems in the author's textbook, they can all be done by using these sample pages from the Nautical Almanac. All right, so let's look at these. And so the first thing we want to do is we want to correct for the dip, or which is also called the eye height. So if you look over on the rightmost columns on page 246, you'll see a bunch of numbers here that we can use these in order to correct for the dip. Now the column over on the left side, so this column right here, these are all really just for large, really large ships. You can see the eye height numbers here are like 20 feet, 30 feet, 40 feet, 50 feet. No recreational sailor is ever going to have an eye height that big. If you're a recreational sailor, your eye height is probably going to be right there. Okay, so we got anywhere from 2, 4, 6, 8, 10 feet. This right here, these are the ones that we're going to be using if you're a recreational sailor. So if you look on problem number 67, it tells you that the eye height is 4 feet. So I want you guys to look in the book or on the screen and tell me, what is the dip correction if your eye height is 4 feet?
1.9.
Okay, now this dash that you see right here is very important. That's there to tell you that it's negative 1.9. You see over here, there are some places where there are plus signs, and then there are other places where it's minus signs. Okay, so the dip correction that we want is negative 1.9. All right, so let's go back then into our worksheet here. And what we'll do is we'll put in a negative 1.9. Okay, so we are now ready to make our first corrected height. Well, this is the one that's called the partially corrected height, which, and also some people call it the apparent height. And so what we'll do then is we'll just do the math. We'll take whatever our sextant reading was, we'll subtract 0.2 minutes for the index, we'll subtract another 1.9 minutes for the eye height. And so when we're done, we get 46 degrees and 11.4 minutes. So this is the partially corrected height, which is very commonly called the apparent altitude. And that's why we call it HA. So that's our apparent altitude. Okay, now it still is not the actual altitude because there's still a couple more corrections that we need to put in. But in order to get these other corrections, what we're going to do is we're going to take the apparent altitude and we're going to use that, and we're going to look in the table and we're going to look up the corrections based on what the apparent altitude is. We don't want to make the corrections based on what the sextant reading was. That's just the way they did it. And I'm sure they had a good reason for doing it. Okay, so when we go to look up what is the refraction correction, we're going to look up what is refraction correction based on what the apparent altitude was. Same thing with the parallax correction and the limb correction. Those are all based on what the apparent altitude is. So let's see where we go. So remember refraction, how that works. So the sun or the star or whatever it is, this is where it appears to be, but in reality, it's actually down here because of correction, because of refraction. So if you go back to page 246 of the textbook, you'll see that for stars and planets, this column that you see right here, okay, so this column right here, this is the column that we're going to use to find out what is the refraction correction. And if you look up at the top here, you'll see that the thing we need to use when we're looking it up is the apparent altitude, not the sextant altitude, the apparent altitude. Okay, so let's remind ourselves. Go ahead.
The Polynesians didn't have an almanac back in the day.
That's right, they did not. It really, it makes you admire them all the more, doesn't it?
Yeah, it does.
Yeah. Okay, so let's go back and remind ourselves what was the angle. Okay, so in the example that we're working, if you look down at the bottom right, our apparent altitude was 46 degrees and 11.4 minutes. So what we do is we find this column and we come down until we get to where we're in between some numbers here. So we see we got 46 degrees and 36 minutes and 48 degrees, 47 minutes. So our number is somewhere in between these two. So we look to the right to see what number is in between those two, and I see a negative 0.9. You guys all get the negative 0.9 there?
Yes.
Okay, good. So that is the refraction correction that we need. Now, so when you look on page 246, I want you to note up at the top here, it says these tables are only good if your apparent altitude is somewhere in the range between 10 degrees and 90 degrees. If your apparent altitude is less than 10 degrees, then there's another table for those, and that's on page 247 of the textbook. Okay, but in our case, that doesn't apply, so I'll skip over it. Okay, so now we know that our refraction correction is that we need to subtract off yet another 0.9 minutes. Now, this is not 0.9 degrees, this is just 0.9 minutes. Okay, next one is parallax correction. Okay, but okay, yeah, all right. So I've skipped over here. Now, in our case, this column here is for the star Fomalhaut. Parallax correction it doesn't apply to stars. So we're just going to skip over that. So we're going to have 0 parallax correction. The next one down here is the moon upper limb correction. And we didn't measure the moon, so we don't need to worry about that. So one thing that's probably worth talking about here, notice in the table here, it doesn't just say refraction correction, it says refraction/limb correction. So why did I say refraction/limb rather than just saying refraction? Well, the reason is because if you measured the sun or the moon, the way that the Nautical Almanac works is it combines the refraction correction together with the limb correction at the same time. So let's suppose we measured the sun, okay? Or okay, so the actually with the sun, you could always measure the upper or the lower, but with the moon, depending on the phase of the moon, if you've got a crescent moon like this, okay, so the moon actually, looks something like this. That's not a very good circle, but you know what I mean. Okay, so let's try that again. Okay, so we can't measure the lower limb of the moon because we can't see it. So in this case, we would have to measure the upper limb. We have no choice. Whereas in this case over here, we'd have to measure the lower limb. We have no choice. And so with the sun, we do have a choice. We could go with the upper or we could go with the lower. Okay. So if we were measuring the sun, what we would do is we would use the columns over here on the left side. And so we would take the apparent altitude and then we would look up what the correction factor is. Now, here's the important thing. This correction factor for the sun includes the limb correction and also the refraction correction together at the same time. Now, in this case, for the example in problem number 67, we're not measuring the sun, but if you were measuring the sun, you would do the limb correction and the refraction correction at the same time. Okay, so let's move on now. And the moon, the reason the table here just says the sun and not the moon is because the moon is more complicated. I'm not even going to attempt to talk about the moon tonight, but before the class is over, by the end of April, we will talk about the moon. Okay, so remember parallax. The idea with parallax is that if you were measuring a star, which is essentially infinitely far away, okay, if you are standing right here, if you point your arm at the star and you've got a buddy over here who just by chance happens to be located at the geographic position of the star, so your buddy points his arm at the star, your arm and your buddy's arm are going to be parallel to each other. So that means that you do not have any parallax error. But if you're measuring the moon, then your arm and your buddy's arm are not going to be parallel to each other. And in fact, that's also going to be true with Mars and Venus also. They're close enough that this parallax error is going to be a problem. And so if you're measuring the moon, the Mars, or Venus, then you have to correct for parallax. But in our case, and by the way, this is how you do it. You look right in this column right here, and it tells you, and notice how it changes depending on the month. Okay, so during some months, you don't have very much parallax error. And then during other months, you're going to have a little bit more. And down here, you can see we've got a lot more. Okay, and so this is where we're going to look it up if that was the case. But in the example that we're doing right now, we're doing Fomalhaut. Fomalhaut is a star, and so parallax does not apply. And also it doesn't have a limb correction, so that doesn't apply either. And the temperature and pressure correction are only for extreme cases, so we're going to assume that doesn't apply either. So we are now ready to calculate the fully corrected sextant reading. And the convention is that we call that HO, where the O stands for observed altitude. Okay, so this is what your smartphone is doing. So if you're using the smartphone, you don't have to do any of this, but since we're no longer using the smartphone, now it's up to us. So what that means is we started off with, this was what the sextant told us. We added these corrections till we got to this, what we call the partially corrected. And then based on this, we then put in a couple other corrections. And so now we finally get to what's called the corrected height. And so this is the actual true altitude of whatever the object is. And so now remember what we really care about is the zenith angle. So when we take 90 minus the altitude, this is the one that we want to do 90 minus. And then when we do 90 minus this, that will tell us the zenith angle. And that will tell us how far we are from whatever star, from the geographic position of whatever star we measured. Okay, so in your homework
say that
tonight, go ahead.
Say that part one more time.
Okay, so remember how when we talked about the theory of how did celestial navigation work, we said that our zenith angle, if I point one arm at straight above my head, and I bring down my other arm until I'm at the pointed at the star, that angle is called the zenith angle. That's the thing that we really want. Okay, but you can't measure that accurately. So what we do is we measure the altitude, and then once we have the altitude, then we just do 90 minus the altitude, and that gives us the zenith angle. So when we do 90 minus, we don't want to do 90 minus the sextant reading. We want to do 90 minus the fully corrected reading. Okay, so HO
90 minus 46, 10.5.
Yeah, that's the one. So that will be our zenith angle, and that will tell us how far we are away from the geographic position of whatever object it was that we measured. All right, so in your homework tonight, well, we've already done half of it together, but only half. So what I want you guys to do to finish it up is I want you to do object number 2, which is Mars. So do the exact same thing. You're going to take the sextant reading of Mars, and then you're going to correct for the index, and you're going to correct for the eye height, and they're going to be the same because the index error doesn't depend on what the object is. It depends on the sextant. And the eye height, again, doesn't depend on the object. So these correction factors are going to be the same. And so then what you're going to get is you're going to get a partially corrected height. And so then I'm going to want you to look up the refraction correction. Now, Mars, you are going to have to do a parallax correction for it, okay? So you are going to have to look that one up. But you're not going to need to worry about this. You're not going to need to worry about this. So I hopefully it'll be straightforward there. And so that's one of your homework assignments tonight, is to do that. Okay.
Did Eratosthenes do a parallax correction in Egypt?
I'm sorry, can you say that one more time?
When Eratosthenes did that early navigation exercise thing, figuring out the circumference of the Earth, did he do a parallax correction?
Yeah, he did not. Now he was measuring the sun. The sun is far enough away that I don't think parallax is going to be a big problem. But yeah, he would have got more accurate results if he had corrected for that. Okay, so let me slip over this really quickly because I don't want to let you guys see the answers. Okay, so problem number 19 is a homework assignment. I want you to do the sextant correction portions of problems 67 and 68. So when you look in your book, you're going to see in 67 and 68, we've measured, well, 67 we've pretty much already done. And so only do the part until you get the final corrected sextant. if you look on here, in fact, let me go back to this page right here. Okay, come on. Oh boy, it's way back here. I didn't think it was this far back. Almost. There we go. Okay. So there is a lot more that we have to do. We are only doing this part of the problem. All of this stuff here and this stuff here, don't worry about these for tonight's homework. We're going to learn about those next time. So on problem number 67, well, we've pretty much already done it. On problem number 68, there's a similar type thing. On problem number 68, we're doing the sun and the moon. Okay, so if you follow through the instructions on those, you should be clear. So those are homework problems for you as well. So let's go back all the way down to here again. Okay, almost. Sorry, okay, there we go. Okay, so we've got a couple review problems down here at the bottom that you might find helpful, okay? Yeah, if you do problems 41 through 55 in the book, that might help clarify some of the concepts we talked about tonight. So these are homework problems. So if possible, use your sextant, go to Utah Lake or Great Salt Lake, take some measurements, try and find your position. I want you to do problem number 19 using the smartphone app to do the math for you. We should probably take a minute and talk about problem number 19. 19 is a little different. 19 is what we call a running fix. Yeah, let's talk about that. So I'll come back and talk about that. So I want you to do the sextant correction portions of 68 and 67, and then these are optional right here. Okay, so let's talk about problem number 19 in the book. It's what we call a running fix. Okay, so what that means is that we take a reading and then we wait a little while before we take our next reading. And in between those two times, the boat was moving. So we need to correct for the fact that we moved in between the two measurements. Now, when you do problem number 19, you're going to let the smartphone do all the math for you. So I don't need to take time right now to talk about how we do that manually. We will talk about it later. But in order for the smartphone to do problem number 19 correctly, it needs to know what direction were you going and how fast were you going in between the times when you took the first reading and the second reading. So the problem tells you that. You know, if you read through the problem statement, it tells you what direction you were going and how fast you're going. So when you enter it into the smartphone, if you just tell the smartphone that information, it can then figure it out. And then next time we meet, we will learn how to do it without a smartphone. But anyway, that's called a running fix if you're moving. Okay, well, it's quitting time and we are pretty much done with tonight's material. Do you guys have any questions you want to ask before we break up? No? Okay.
No, thank
All
you.
right. My pleasure. So everything we did tonight was recorded. And did you guys receive the link that I emailed to you for the
Yes.
recording lesson? Okay, good. So it takes a couple hours to process the video, so I won't get it to you tonight. But by tomorrow morning, I'll send you the link for tonight's video so you can go back and rewatch anything on. All right, well, I'm going to go ahead and end the meeting then. I will
Thanks, Doug.
see you guys next week.